Okay, so here I'm going to construct the Born-Haber cycle for cesium solid plus chlorine gas going to cesium chloride. This is the enthalpy of formation of cesium chloride. So first step in your Born-Haber cycle, you need to start with the reactants in their standard states. So I'm going to draw a line to represent the energy here. And I'm going to draw and write, cesium solid in its standard state. And then half Cl2, because I'm only using one Cl in the product. Cl2 gas, cesium solid in their standard states. I've been told that the enthalpy of formation of cesium chloride is minus 433. So it's always good to draw your reactants and then secondly draw your products afterwards. So I'm going to draw the product here. I know it's exothermic because the question has told me, so it's going to be lower down. But generally you can assume that the enthalpy of formation of an ionic solid is always exothermic. So my product is cesium chloride. Cesium chloride solid. You need state symbols at all points for this. And then I'm going to draw a downward arrow to show formation from reactants to products, and that's minus 433. Okay, it's good. I've got where I'm starting and where I'm ending. Now we're going to do the bit where we do the cycle. The first step then is to atomize cesium solid into cesium gas. So let's do that. That is going to require some energy. So now I've got cesium, no longer a solid, it's now a gas. And then nothing's happened to my Cl2. That's just still a gas. And that has cost me how much? Plus 79 kilojoules per mole. So I've got cesium gaseous atoms now. And now I need to make chlorine, which is a diatomic molecule. I need to make that into a monatomic gas. I need to split it up, atomize molecular chlorine. So that's going to require some energy to make. Now cesium, I've got gas. And now I've got 1 mole of chlorine gas. How much energy is that taken up? Well, the enthalpy of atomization of chlorine is 121 kilojoules per mole. I am atomizing half a mole of chlorine to make 1 mole of chlorine atoms. So the enthalpy of atomization stays the same. It's plus 121. I do not divide it. Plus 121, because the enthalpy of formation of enthalpy of atomization, is the value to form 1 mole of chlorine atoms, which is what I've done here. So it's plus 121. And then the last endothermic process is going to be quite an expensive one, because then I've got to ionize my cesium to cesium plus, because it's a cesium plus in the product. So I'm going to rip an electron off cesium, and that's going to give me cesium plus. Remember, we're in gaseous form. And I've got my chlorine gaseous atoms, and the data there has shown me that that costs me plus 376. So it's plus 376. Great, so that's the endothermic stuff done. I'm now going to continue my line along the right, and now I'm going to start with the exothermic stuff. So exothermic, I need the electron affinity now of chlorine to make chloride. That's exothermic. Okay, so I'm going to draw a line to represent the energy. So I've still got cesium plus, and now I need chloride. Again, state symbols at all times, and that is minus 346. That's the electron affinity. And then finally, my lattice enthalpy. Lattice enthalpy is the formation of lattice from its from gaseous ions. So it's respective ions in their gaseous states, and that is what we want to find out. So that's delta H lattice enthalpy. Okay, so now I've got my Born-Haber cycle. That's it right there. Now we need to put this into an equation. So I know the overall process is minus 433 to go from there to there. And I also know some of the values going the other way. So I need to equate these two routes to find the unknown. So I'm going to do minus 433 is equal to this plus this. So I've got 79 plus 121 plus 376 minus 346, and then plus whatever delta HLE is. Delta HLE is a negative value because it's the formation of a lattice. So it's always going to be exothermic. So I can do plus there, and then I'll get a minus number for this when I rearrange. I'm going to make these all into one number. Minus 433 is equal to 230 plus delta H lattice enthalpy. That stuff just sums to 230. I then rearrange the equation. Delta HLE is equal to minus 433 minus 230, which is equal to minus 633 kilojoules per mole. Should put there. Okay, so I've used the Born-Haber cycle. I've gone from enthalpy of formation and these other values to find the unknown here. I've equated the two, and I've got minus 633 kilojoules per mole as the enthalpy of lattice formation. Enthalpy minus 633.